let's have a look at the new Generation 3 Tekin speed controls. Improved in every way, they say. Now, as normal with Tekin, they offer two versions in every wind. And these are the 17.5 turn. They do an RPM one and one which they say is normal, which I assume has more torque or something. I've got one of each. This is what it looks like. It's completely different from the Tekin that went before. It's got a lot of big openings. You can see all the coils inside, and it's all aluminium. It's got an aluminium end, and there's a scale from 0 to 60 degrees with a tiny little notch on the end. 3 screws hold it on the end. It's been shimmed, not too bad, it's not tight and it's not really loose, so that's quite good. Chamfered front edge so that you can get it on your top deck, hopefully, quite well. Big head screws here won't round out easily. They say it's 158 grams. I did weigh it and I found it was 160 grams, so pretty close. I mean, the weight is going to vary depending on the winding and the thickness of the wire, so there's bound to be a few grams difference. Winding looks pretty neat these days. Hopefully it's high temperature. You can see the ends of the stacks, so you can measure the stack length, which I can do. Just use a vernier. You can get it on the end of the stack and measure it. 20.74 about. Now, what's the difference between the RPM and the normal one? Well, looking at their specification, I copied this off of their website. You may not be able to read it. So it talks about the rotor size on the 21.5, 17.5, 13.5. It says it's 12.5 millimeters, and doesn't mention. It says 13.5 RPM, and it's got 13.5 as well, and 17.5 RPM, 17.5. It just says 12.5 millimeters, so that doesn't help. But if you look at the data on their tuning rotors, they've got a 12.5 millimeter spec rotor blue and a 12.5 millimeter spec rotor strong yellow. So you can't actually see through. There's a metal plate there. You can't actually see the color of the rotor, so I'll take it out and have a look. This one's got some sort of glue on it as well, which I didn't put on there. I don't know whether in manufacture it's not very good. Hopefully that'll come off. And I'll test it on I'll test them both on the motor analyzer and compare the RPM one to the normal one, see what the difference is. And I can do some other checks as necessary if I take the rotor out, see what strength they are. And I've already had one look at this and set it to 45 degrees on the end bell, and the actual notch is very close to 45, so hopefully that's quite accurate, that end bell. Some manufacturers, the end bell markings are way out. So I'll run that up. I've got a big LiPo I've charged up. If you're going to do comparison tests, you have to make sure that the voltage, especially if you're measuring the kV and everything, voltage remains as close to equal when you're testing. They don't draw a lot of amps as you're only running it for a short time, so if you charge one of these up, you don't want to run it when it's fully charged at 8.4, because the voltage will drop early on in the bit of use, so you could start off with a high voltage and then drop down. So either run it a little bit or don't fully charge it. Anything over about 8 volts is fine. So I'll just set this up for some tests and record the tests as we go along. I've taken the end off the standard one, not the RPM. It's got a nice big bearing, very nice big bearing, and some shims for the shimming. Also the screws just hold the front on a tiny, they don't go all the way through like most motors, so they're just tapped into the end of the case. So that come off like that. Now inside you can see there's yellow, I think that's yellow, rotor end marking. According to the specification, yellow is the 12.5mm spec rotor strong yellow. So I expect when we open the RPM one, we'll probably find the 12.5mm spec rotor blue. I've got a Gauss meter here, which I'll just check the Gauss and see what it is. So we just take the rotor out if we can. If it's a bit tight, I've got some special pliers. I've got these special pliers. They've got a groove on one of the jaws, and they're also parallel operating, so that they don't just hold on the tip and they're flat on the other side. Very useful because you can put the flat onto the flat on the shaft, and the round bit goes around the other side, so you don't damage it at all. And you get really good grip, and you can pull it out like that. And I've got the Gauss meter here. You just zero it best you can, and then you just remember, never put these rotors down, because they can be attracted to other metal objects and they can go flying. So you just let it go in under its own power like that, and it's reading 1392. If you rotate it 180 degrees, it should, if it's a good magnet, read the same. 1355 is quite close. If they've not made the rotors very well and the magnetic material has been offset due to cheapness, you can sometimes get a much stronger magnet on one side to the other. You have to make sure it goes in. This is really tight. This hole's only 12.5, so it's just a real tight fit. So it's about 1374, and you can twist it to find the high spot as well. It's pretty close on both sides, very good quality. You can also see you can't see, but there's some little drilling on this aluminium. This is aluminium that's been pressed on, and they drill that to try and balance it, because you can't drill the magnet because it's rock hard sintered, and if you do it just shatter. So that's the gold one, 1370, about 1370, and we'll measure the other one when I take it out as well. By the way, we can check the diameter as well while we're at it. Try and get it dead square. 12.47. 12.5 is the max, so they pretty much keep him as big as possible. That's really strong. Okay, I'll put it back in the motor. I can also just have a look inside. This looks pretty good. Windings are pretty neat. I can also measure the resistance, which I'll do that again in a minute. Before you put the rotor back inside, just make sure, look inside, make sure there's no shim's fallen off. This one did actually have a shim inside, and it was just down by the bearing. You just have to tap it out. If it gets stuck inside, if you can't get it out, you'll have to take the end bell off. But normally they drop out if you just tap it. But it's very important that if you get one left inside there, it can get all mangled up and it can break the sensor board. One thing with this new end bell design with these very small screws is it's not the end. This face is not keyed to the body at all, so you have to hold it very, very tightly and align the holes up in the where the screw's going to go in, and you have to be careful that you don't start screwing it in sideways or something, because it relies on these 3 screws to locate in the end of the can and then pull this up tight and square. So normally they cut a groove, some other manufacturers, a very small groove, so you can feel it snap into position. This one just slides about on the smooth face. But anyway, once, if you're careful, also you don't lose these screws, they're pretty small compared to the long ones, some others. And then you obviously just tighten them up equally, don't over tighten, and check the end flow. If you've lost any of these shims while you've been messing around with it, this would be won't have have too much end flow, or if you've got a shim inside that if you didn't see and it's jammed, you won't be able to move it, and then just flick it over. So okay, we'll test the winding resistance. Tested the winding resistance. I've got this very accurate low ohm meter. It's pretty old, like most of my stuff. It's very accurate though. I have got another one like this one, which also can measure very low ohms. But this is the best one. I've got plenty of readings here. 17.5 turn. A typical ohm is 0.045. So we just put the clips on. Some are more difficult than others. You've got to get both sides of the clip on. 0.045. You can see that. So the winding resistance is exactly nominal. You can check all of the reading 0.044. I don't know if you can see that. You can check all 3 coils, which if you think you've blown your motor, that's one way of checking them. But on a new one, you'd expect them all to be pretty much the same. 0.0, let's just 0.044 is close enough. So it's pretty standard. For purposes of comparison, I've set the end bell to 45 degrees so I can compare it to lots of other readings that I've taken on other motors. End bell readings 44, average is 45, and it's got a 44, 48, 43, so that's pretty much, a lot of motors have that sort of spread. If you get one where they're all 45, you've got a good one. So that's the timing. So now I can do the kV reading. Let it stabilize, and then we hold the readings. Okay. With this battery voltage is 8.0, it's drawing 3 amps at 45 degrees. So I'll just make some notes. It's drawing, it's got a kV of 2500, RPM 20,000, It's all nice round figures on this. It's drawing 3 amps, and that was a test voltage of 8 volts. I'll write it down on this piece of paper so we can compare notes for the yellow rotor. Better put it's Tekin 17.5 turn, so that we can compare. So I will do another test in a while. I'll put the amps up to about 6 amps and see what timing we get for that as well. But so that's that one, and I'll unbox the other one and check that, the high RPM one. Okay, we've got the high RPM one in this box, and just get it out. And I noticed that glue on the other one, it's on this one as well. They put this blob of glue quite strong, and they've stuck the motor into the bottom of the case. I noticed they do this with their speed controls and also their hot wire, and I've had people rip the case off the hot wire trying to pull it out off the glue. This is really quite quite a blob. Anyway, I'll probably take that off. It comes set out the box. There's a notch on 10 degrees of timing, so that's probably for safety reasons, so that if it come out the box like some of the Trinity ones from 50 degrees, and then you go and put a speedo on it that has some advanced timing, they probably have run risk of blowing them up. With on 10, even if you put your boost on maximum, it's gonna survive. So that's probably why they do that. Anyway, I'll have a look at this, test the rotor and everything like we did on the other one. Quick test measuring the winding resistance. I expect it to be the same, and it is. It's reading about 0.044. Exactly the same as the other one, so I didn't expect there to be any difference there. I've adjusted the M bell to give me 45 degrees, and you've got a spread on this one, 43, 47, 44, so it's about the same as the other one. So 45, we can do an exact measurement copy now. By the way, on the M bell, when I adjusted it, it's now showing about 50 on the M bell. The other one was dead on, so the M bell markings are not 100% accurate. So let's just do the KV. Let it stabilize. And this is supposed to be the high RPM one, remember. Now, here are the results. If you can see them. Before we had 2,500 kV, 20,000 RPM at 3 amps at 8 volts. So there's the 8 volts, 2.7 amps, which is less. The revs 20,091, and the kV 2511, which is virtually identical in every way. I mean, if you had these two motors and you measured them, and you would say they were the same motor. 2511, 20091. But 2.7 amps is slightly less. 8.4 volts. I've written down the results so we can remember them, and then I'm going to take the rotor out and see what colour it is and measure its strength, and then we'll bump up the kV, try and find the 6 amp point and see what we get when we do that. Checking the stack length. It's important that you get it on the lamination ends and not on the plastic former that might be around it. This is the RPM one, and it's reading 19.59. You can get two readings, I think. Which one did we do? 19.42 or 19.46, 19.47 about. So 19.54. So it's about 19.47, 19.54. Just write it down. And on the other one, it was we did measure it before, but it's 20.31 and 20.38. Which one is this? 20.31, 20.38. Yeah, I'd made a note before, so 20.32, 38. So the RPM one looks like it's got a lamination less. Checking the weights. This is the RPM one. It weighs exactly 158 or 157.9 grams, and the standard one weighs 160.2. Now the RPM one has about one lamination less. That would account for a little bit, and also the got to take the rotor out and look at it. I didn't weigh it's difficult to weigh the rotor. It gets stuck on the affects the scales, but we measure the grouse, so the rotor might actually be slightly different in weight as well. I've just taken the front off of the RPM one, and you can see it's the same yellow or gold rotor inside. So we can just measure the Gauss. Just pull it out with these pliers. Be careful. There's a little shim. Come out with it, and it will be on the end that's come off. So be careful not to lose that. Put it in here. (1403). Try the positive pole. 1404. So it's actually a little bit stronger than the standard one. I guess these rotors. Let's put that down. Rotor strength. The RPM one, so it's yellow as well, and it's 1405 Gauss. The previous yellow one was in the normal one, measured about 1375. This is 1405, so I'd say they were the same rotors, just a small variation. You can check the diameter. Let's turn this on. 12.46, 12.47. That's exactly what we measured on the other one, so it's definitely the same rotor. I'll write it on there, 12.47 millimeters. 12.47 millimeters. The other one was exactly the same. So I've written down all the specs, and at the moment, except for the stack is on the RPM one is slightly smaller stack, and the weight is slightly less on the RPM one as well by a couple of grams, which won't be the rotor, so it must be just due to the less laminations. But on the test we didn't really get much at 45 degrees, so I'll ramp it up and see what we get. Right, I've adjusted the M bell on the RPM one to near enough 6 amps that I can get, so So we can compare the readings when I do the other one. So I'll just ramp this up. Let it stabilize. Just show you. You can see. 2861 kV, doing 22,605 RPM, drawing 6 amps at 7.9 volts. So if I write down those figures on this piece of paper, and we can compare it to the other one. Now on the N bell, I had to get that sweet spot reading. It's just under the 60-degree mark. Moving it just slightly one way or the other makes a big jump. So when you start setting your M bell around about this mark, be careful, because if you turn it up just to where it says 60, you'll probably be drawing about 12 amps. So it's quite critical. And the timing to get that on the RPM motor, average 52 degrees and 51, 54, 51. So the timing is actually tightened up a bit as we've gone higher. And that was for the 6 amp reading on the RPM one. I've just run up the standard motor on the tester to get exactly 6 amps so we can compare, and just show you the results. You can see kV 2740, RPM 21651 at 7.9 volts and 6 amps. So I'll just write that down on this paper and then we can compare them. So 2740, 21651, 6 amps, 7.9 volts. So the RPM one did get a few more revs at the same current. The kV was a little higher, the revs a little higher by 1000 RPM. So not a huge amount. Maybe we get better results on under load. I put it on my load dyno over there and see if we can get any more significant results. But the difference is very small. I'll just check the timing that we ended up. On the first one, the timing was 50, forgot to write it down, wasn't it 53 degrees? Let's just check that this one is. Just change it to the timing. On the M bell, I've set it about, it's shown about 50 I think on the end. The other one on the M bell, it was twisted right round to nearly 60 to get the same result. Showing 52 and the spread's 52, 55, 49. So I'll just write that on there. This is the standard one. So we had 52 degrees on the M bell. And the spread's 52, 55, 59. Let's have a look at the end. Yeah, the notch, it's hard to see. The notch is just, there's a little line on the end. It's just past that mark, which was the 50. So this M bell on this motor is pretty accurate. I think the one on the other motor was a bit out. So that's the best results we can get with the testing. The difference is minor. If it had a different rotor in it, I think the difference would be huge. And as I said, they do list different rotors here. They've got both at 12.5 millimeter. They've got a spec rotor blue and a spec rotor strong yellow. So I would have thought the blue would have been in the RPM one. I don't have one of those rotors at the moment, otherwise I could have put it in and see what it did. I just double checked the timing for the RPM one. to see what, when we got that 6 amp reading, what it was, and it's also 52 degrees. So the difference in these motors is so small to get the same result. Both of them measured 52 degrees, and so now I've got all the results on here now, including the 52 degrees for the standard and the RPM one. The final test on these Tekin Generation 3 17.5 turn motors. I've got the RPM one in there. This is the standard one. I've set them both to exactly 10 degrees on the motor analyzer, though on the end bell they were slightly different on the two. I've got the flywheel on here, which gives it a bit of a load, and I can measure the RPM and the current draw on here. I've got the blinky speed control, and I've got a fully charged battery, and at the control here I can set it from, I can turn it, whack it up to maximum speed and measure the RPM. Now what's the current jump on here as well? So here we go. 16,870, drawing 2.1 amps, 8.21 volts. Just do it again and watch the current jump at the start, see what it goes up to, flip it to maximum. It's about 30 odd amps, do it again. 37 amps that jumps to at the start, one more time. 34. So we've got those readings. I just need to write them down. So this is the RPM one. I'll just write it down on this piece of paper. It did a 37 amp and then steadied at say 2 amps. It was the RPM was 16,870 RPM. The voltage was staying steady, and the final amps was 2.16 amps, and it was 37 on the jump. So I'll put the other one in there and just see if we can see any difference at all. I've swapped the motors over, I've taken the RPM one out, put the standard one in, everything else is the same, time is 10 degrees, and blinky, motor, speedo, everything's the same. So let's just ramp up the speeds. The RPM one gave 16,870. 16,429. And the current was 2.1 amps. 16,429. Just do that again because it happens a bit quick. Now watch the startup current as well. 43 amps. About 2.2. 16,429. That's 2.1 amp. And the startup current was higher, about 43. Depending on how quick you do it, it's over 40, so about 47 amps. I think that's quite a lot more than the other one. So the results show that the RPM one actually does give you a bit more revs than the standard version. At the full revs, current 2.1, I wrote 2.16, but the current jumps around a bit, so I'd say that they were near enough to be the same. Startup currents, well, I had higher on the standard than the RPM one. It does depend on how quickly I turn the knob, but it did seem consistently a bit more on the standard one. But Besides that, if you had them in your car, one or the other, I doubt if you could tell any difference which one you had. So other manufacturers also make versions of the motors, such as Trinity. They do standard, and they do a 1S version. The 1S version is basically the same as this one. The RPM one, it's got a short stack, and on the 1S Trinity ones, they've got short stacks as well. So that's how they give you two different ones. Unless they have totally different rotors in them, I very much doubt that you're going to notice hardly any difference at all, as the rotors are the thing, there's magnetic strength, etc. And if you had a different winding, of course, are the only things that really make a major difference. So that concludes the test, and I hope it's been of some use.